Hi everyone, we're going to do lesson 40 on chi-square tests for goodness of fit. Is this the distribution or is it something else? Now we've actually already done a simple version of this kind of test back when we were doing tests for P, a population probability or proportion. That was back when we had binomial experiments. But now we're going to extend to multinomial experiments. First of all, let's do a review of tests for P and binomial experiments. So back in lesson 34, we discussed hypothesis tests for P, once again, a population proportion, or success probability. So for example, a binomial experiment could be flipping a coin n times, right? P could be the probability of heads, for example, on the coin. Maybe heads is a success. The null could say P equals 0.3, for example. Maybe the null says that the probability of heads is 30%, in which the case the failure probability, Q, is 70%, or 0.7. The alternative would say that P is not 0.3 in a two-tailed test, right? Now, again, this is an example, a basic case of a goodness of fit test where you have two categories, success and failure. Two possible outcomes, success and failure. The probability of a success is P. The probability of a failure is Q. Or you could use different notation. You could say P sub success and P sub failure. And these probabilities add up to 1. So the null hypothesis would correspond particularly to this distribution. The probability of a success is 0.3. The probability of a failure is 0.7. If you don't like this for a coin example, we could have that P is the probability that it will rain on November 1st. November rain, old Guns N' Roses song. All right. In a binomial experiment, a trial, such as a coin flip, has two possible outcomes. Again, success or failure, maybe heads or tails. So now we're going to extend from a binomial experiment where you have two possible outcomes or categories to multinomial experiments where you could have more than two possible outcomes or categories. Again, a multinomial experiment is similar to a binomial experiment, except that a trial, such as a die roll, has more than two possible outcomes or categories. So in this multinomial experiment, rolling a die n times, let P sub I be the probability of a magician's die coming up I, where I could be one of the 6 die faces. The null hypothesis says that we have a uniform distribution on the die faces, meaning that the probability of getting a 1 on the head, P sub 1, is 1/6. The probability of getting a 2 on the die, P sub 2, is also 1/6, and so forth. So in other words, P sub I equals 1/6, where I takes on these various indices. So the null hypothesis says the distribution is uniform. The alternative hypothesis covers every other possible case. The distribution is different. In one way or another, the distribution is different. Whether you have a higher probability of 1s or 6s or whatever, the distribution is somehow different. It's not uniform. Once again, the null hypothesis is the basis for our calculations. Let's do an example. So in example 1, each trial has 3 possible outcomes, which we will call categories. Example 1, chi-square test for goodness of fit with respect to a particular distribution indicated by the null, which may or may not be the claim. 10 years ago, 50% of the registered voters at a college were members of the gray party. I'll go ahead and I'll put that in gray. Sure. Let's put that in gray. 50% of the registered voters were members of the gray party. 40% were members of the yellow party. And 10% were neither. What's neither? How about purple? Purple's like neither nowadays, right? 10% were neither. Test a claim that, I'll put this in red. Test a claim that the party registration, well, may as well put blue. Text is blue, may as well put blue. All right, test a claim that in blue, the party registration distribution at the college is the same now as it was 10 years ago at the 0.05 significance level. Of course, that's alpha. Fishy. Now before, when we had a test for P, we could just talk about P as our key parameter. But now that we have 3 categories, we have to talk about at least 2, and we should write all 3. It's convenient to write all 3. Instead of going like, P, Q, and 1 minus P minus Q, let's do 3 good notations here. Okay, let P sub G equal the proportion of registered voters now at the college who are gray party members. So P sub G, gray party. Let P sub Y be the proportion now who are yellow party. The proportion now, not 10 years ago necessarily, but now. P sub Y, yellow party. Okay, and P sub N, proportion now who are members of neither. Okay, so 3 population parameters here, P sub G, P sub Y, P sub N. Before, in binomial experiments, we had P and G, and P and Q, and we could focus on P. With more than 2 categories, we really should have notations for all the different probabilities or proportions for all the categories. Okay, setup. See, before we just had P equals 0.5 or something, and that implied what Q was, right? Now we're indicating the hypothesized values for all 3 parameters. The null hypothesis says, wait, what did the null hypothesis say? Okay, oh, well, what did the claim say? The claim said that the party registration distribution at the college is the same now as it was 10 years ago. That indicates a sense of equality, and that's going to be the null. The null hypothesis is going to correspond to a particular distribution. What was the distribution 10 years ago? Well, 50% gray, 40% yellow, 10% neither. So the claim here, based on the wording of the problem, corresponds to the null, which posits a particular distribution. P sub G is 0.50 or 50%, like 10 years ago. P sub Y is 0.40 or 40%, like 10 years ago. P sub N is 10% or 0.10, like 10 years ago. The null claims that the distribution now is exactly the same as it was 10 years ago. We might be going, oh yeah, isn't there probably going to be some difference? Well, remember, the idea is, are we going to reject the null or not? Do we have enough evidence against the null? Remember, the null has some resiliency here. I know it looks hard to really hit this on the mark, but in a way, in order for the nulls to survive, these don't have to hit on the mark. As far as the null goes, he just doesn't want to be rejected, right? The poor null just doesn't want to be rejected. Anyway, the claim here is the null. In other cases, the claim may be the alternative. The alternative hypothesis, H sub 1, says the distribution is different. And for these goodness of fit tests that I'll deal with you, the alternative hypothesis will always say that. The distribution is different from what the null hypothesizes. Alpha was 0.05. That was given in the problem. Now you might be going, wait a minute, what type of a hypothesis test is this? Is it two-tailed, left-tailed, or right-tailed? Well, if you have a type of hypothesis test, well, where the alternative is saying that the distribution is different, right, like in this goodness of fit test, then that's going to be a right-tailed test, Now before, in the test for P, different meant just the is not equal to symbol, which implied 2 tails. Okay. But here, actually, the tests in this lesson, these goodness of fit tests, are going to be right-tailed, which might surprise you. Okay, and I'm going to explain later on why it is. that these hypothesis tests are going to be right-tailed. In fact, when you get beyond tests for standard deviation and variance, the chi-square test we're going to talk about in our class will be right-tailed. Okay. So that's the setup. I've been talking about the setup and an example here. Let's conduct the test. Let's actually talk about the sample data and what we do with it next time.